Okay, now we're going to move on and start looking at integrating things like sine cubed kx and cos cubed kx. Right, so the first example we'll deal with is integrating sine cubed, let's go 4x dx so we don't get confused between the power and the angle. Right, the beauty about sine cubed and cos cubed is that we don't need to memorize any formulas, etc. What we do is split sine cubed up into sine 4x and sine squared 4x. Okay, that's fairly obvious. Now what we do is actually change whatever the squared one is into its partner due to the identities. Now sine squared plus cos squared is 1, so sine squared must equal 1 minus cos squared. And we leave the angle as it is. This now should start looking familiar because you now have two terms, a simple one and a slightly more complex one. So we're going to go with the old change of variable. So let u equal cos 4x, okay, just the inside of that and not the whole bracket but just the trig value. As soon as we let u equal, the next line is du dx equals. So the derivative of cos 4x is negative 4 sine 4x. So now we go back to our expression as we do a change of variable, and we're going to rewrite it all in terms of u, du, dx, etc. So here's the sine 4x. Right, there's the sine 4x. So that sine 4x is actually equal to negative 1 on 4 du dx. Alright, then you've got your 1, then you've got your minus. Now cos squared is actually u squared, and you've got your dx. Take out the negative a quarter, and you've got yourself an integral of 1 minus u squared du, because the dx's have wiped each other out, negative a quarter. We're now anti-differentiating 1 minus u squared in terms of u. So the antiderivative of 1 is u. The antiderivative of u squared is u cubed over 3. Plus you've got some sort of constant. Let's call that c1. We're going to multiply back in and we're going to replace u with cos 4x. So we're going to get negative a quarter of cos 4x. Then we're going to get plus cos cubed 4x over 12, the 4 and 3 making 12, and then you've got c as the constant. Let's go with the same thing, except this time we'll take another value. So what did we do before? We did sine, let's go with cos. So let's say we're asking to do cos of cubed of 2x on 3. Let's make the angle more complex. Okay, so that equals cos 2x on 3 cos squared 2x on 3 dx. Cos 2x on 3. Next line, 1 minus sine squared 2x on 3. This time u will equal sine of 2x on 3. Right, whatever squared, that's what u is. Find the derivative. The derivative of sine 2x on 3 is 2/3 cos 2x on 3. Time to rewrite the expression. There's your cos bit, there's your cos bit. So obviously to get that by itself we'll transpose, so this becomes 3 on 2 du dx. Then I've got my bracket, 1 minus u squared dx. 3 on 2 comes out. We're actually integrating 1 minus u squared du. Gives me 3 on 2. The antiderivative of 1 is u. The antiderivative of u squared is u cubed on 3 plus a constant c. Multiply back in and replace. We get 3 on 2 sine 2x on 3. And we get negative. Now 3 on 2 times 3 cancels, so we get a half sine cubed 2x on 3 plus a final constant. So what was the pattern? We anti-differentiated cos cubed, we ended up with sine and sine cubed in my answer, and originally when we anti-differentiate sine cubed, we ended up with cos and cos cubed in our answers. Okay, so patterns as always. Let's have a look at a complex example of integrating sine squareds, cos squareds, etc. If I wanted to integrate sine squared 3x cos cubed 3x dx. Okay, so we have a look at this and we think to ourselves, oh, we've got a product of two functions. Is it possible to use change of variable? Problem is that one's got a power 2 and one's got a power 3. So we're not going to get an exact match with the derivative of one being in terms of the other. Very rarely do we change squared terms, so let's not look at that. The thing about cos cubed, what we'd normally do with cos cubed is write it as cos 3x and cos squared 3x dx. Okay, well, hasn't done much for us at the moment, not real exciting. Let's turn around and change cos squared into 1 minus sine squared, because that's what we normally do when we're dealing with cube functions. Okay, now I'm starting to get a little bit more excited because I'm seeing a sine squared, I'm seeing cos, and I've got another sine squared in here. Now if we were normally dealing with a cos cubed, we at this stage would write that u is equal to sine 3x. Then immediately we would find the derivative, which would be 3 cos 3x. Let's go back to our original expression. Sine squared. Well, since u is sine 3x, sine squared 3x can be written as u squared. That's good. Got rid of that one. Cos 3x. Oh, here we go. There's cos 3x. Cos 3x is 1/3 of du dx. Good stuff. Then we had a bracket. We had 1 minus, now sine squared, well, we had called that u squared. And we got the little dx dude sitting at the end, which we'll wipe out in a second. So I can pull out the third. I've got an integral. I've got u squared 1 minus u squared du, because the dx's have wiped each other out. That's equal to 1/3 integral u squared minus u4 du. So we get 1/3, running out of room, square bracket, the antiderivative of u squared is u cubed on 3, the antiderivative of u to the 4 is u to the power of 5 on 5, plus the little constant, which we come to expect and love. Multiply back through, you're going to get 1/9 of u cubed, but u was sine, so that's sine cubed. Then you get negative 1 over 15, 3 by 5, 15, u to the 5, so that's sine to the 5, 3x. And then you had 1/3 of c1, which we're now going to just call c. And there you go, a complex looking expression, sine squared, cos cubed. As long as the angle was the same, which it is, we can proceed through using a composite of two types of functions, but ultimately it's still a change of variable, and that's it.